Syzygy, episode 42, Life, the Universe, and Everything. Well, it is episode 42 of the Syzygy podcast. My name is Chris Stewart. Sitting opposite me, as ever, Emily Brunsden. Emily, the number 42, what does that mean to you?
It means life, it means the universe, and it means everything.
Of course it does.
And it means a fantastic series of novels.
It does, by the fabulous and dearly missed Douglas Adams. You read the
Of course.
The Hitchhiker's Guide to the Galaxy,
poured over
increasingly
them.
badly named trilogy. What did it get up to? 5 books? 6
Yes,
books?
yeah.
So the fourth one was called the fourth book in the trilogy, and the fifth one was called the fifth book in the increasingly inaccurately named trilogy, which I quite liked. Look, if you haven't read the Hitchhiker's Guide to the Galaxy 5-book trilogy, then look, pause the podcast now. Go and read them all. We're not going to go in depth on it. You don't have to, but I think it's safe to say that for, I was about to say people of a certain age, but I think it probably transcends age and is sort of an absolute classic of the, I don't know, the comedy sci-fi genre. Is that even a genre? I don't know. It's weird. It's fun. And it kind of makes you think in a slightly different way about the universe. When did you first read The Hitchhiker's Guide?
Oh, it was probably when I was an undergraduate, actually.
Yeah.
So I got really into them. And of course, it complements astrophysics really nicely. It takes all these ideas about the universe and just sort of turns them around, puts them on their head, and then you've got to sort of think about them.
It does. It does. I mean, Douglas Adams had a wonderful way of taking really, quite deep ideas in science and technology and then just upending them and taking the living piss out of them and turning them into comedy gold. And as someone with a scientific bent, you'd be reading it and it would just make you laugh out loud because you'd spend all of this time taking on the actual science, and then to see someone just turn that around for comedic effect was a lovely moment. And he was utterly bent. I actually started reading it to my kids a little while ago, and then I realised, I probably need to give this a couple more years. It's just going over your head. Anyway, we're not going to do a big review of that, but we figured episode 42, we really kind of needed to pay homage to that. The number 42 comes up a lot in the book. It's a central part of the book. It's the answer to the big question of life, the universe, and everything. The issue being, of course, what actually is the question, if the answer is 42? Anyway. Episode 42, we need to talk about life, the universe, and everything. We need to talk about life in the universe. Have we spotted any yet, Emily?
No.
Well, I mean, other than ourselves.
No,
we haven't seen anything. In fact, I think some people would even debate whether or not we've seen intelligent life in the universe, including ourselves. But we haven't seen any other life. It hasn't stopped us trying, though.
it hasn't. And what we're going to be talking about today is kind of how do we think about how likely it might be that life is out there in the universe. And it's a particularly famous equation that we talk about. And this equation is part of a lot of astronomy courses, education courses. But I actually think it's a really good thing for everybody to try and wrap their heads around.
It's a really interesting exercise, isn't it? Okay, so this is called the Drake equation.
The Drake equation.
All
yeah.
right. So that's what we're going to be talking about today. We're going to be working our way through that one. Who was Drake?
So Frank Drake was an astronomer who was really, really interested in the question of, is there intelligent life in the universe?
Other than ourselves, which, as I said, is debatable.
Well,
but there we
yeah.
are.
I mean, let's just take that as read,
All
right?
right. We've got one.
So in 1961, he proposed this equation. Now, it's not a research equation. It's not like, Newton's third law or Einstein's E equals mc squared.
This isn't a law of the universe. It's
yeah.
not, we can measure to 3 decimal places how many life forms there are in the universe. This is an estimate.
Yeah, so this is actually an example of a Fermi problem, although the concept of a Fermi problem, I think, came a bit later. So Fermi problems are basically how do you make a coarse estimate of a very, very difficult to guess number.
Named after the famous physicist Enrico Fermi, who apparently was really good at doing this sort of thing. And so while other people would go away and do incredibly detailed calculations of, atomic physics and things like that, Fermi was really good at saying, hang on, but we know this and this and this and this and this, multiply that, divide by that, add the 3, carry the 2, and you've got 5. And so we should have 5. And the really complicated calculations would come back and go, yeah, it's 5.8. How did you do that? And Fermi was just really good at these back-of-the-envelope style estimates based on really good guesses and known quantities. So they became known as Fermi Fermi problems. How do you estimate, I don't know, the number of piano tuners in New York is a classic example. The sorts of assumptions you'd need to make to figure that one out, and you can get pretty close. This is a Fermi problem about, so if you were to look up into the night sky, look at our galaxy, how many life forms should there be?
Yeah, so very specifically, it's an estimate of the number of currently active, communicative alien civilizations in our galaxy.
All right, so there's a number of things in there, and there's a whole bunch of different assumptions that would need to go into that. I mean, I guess this is coming from a place where, as a species on Earth and looking around and seeing a whole bunch of other species on Earth, none of whom are looking through telescopes and wondering about the night sky, at least that we know of. But we all came from the same kind of stuff. We all climbed out of the primordial soup, as it were, genetically together. So life, we know, has occurred in the universe at least once. But is it exactly once? And it's a compelling question. Surely we can't be alone. So let's try to figure out, all right, based on what we do know, could we make a solid guess? Should the universe be teeming with life? We just haven't seen it yet. Or is it actually possible that we're the only ones in our entire galaxy, or possibly anywhere? So how do we work our way into this? What did Drake do in order to start making these estimates? What did he write down on the back of his envelope?
Okay, so it's a fractional probability problem where you multiply all the probabilities of certain things happening and you get a number at the end, which is the number of civilizations that you expect to find.
Okay.
So there's 7 parts of the Drake equation, and we can run through each of those. I've got the numbers here in front of me for how we estimated what those numbers might be in the 1960s, which is when Drake was looking at this, and also it's kind of what we know today, because some of these numbers we have actually been able to pin down rather accurately.
Yeah, I'm guessing things have changed a bit in the last 50 odd years. Yeah.
Yeah, so that's quite nice.
What do we have to do? How do we get to our final answer? What is our final answer? What are we trying to get to?
So we're trying to find out the number of active civilizations that are going to be in our galaxy.
Okay, so let's call that what? N?
N.
N
Yep.
is the number of active civilizations in our galaxy. All right, so it's going to be N equals what?
So we have N, the number of civilizations, equals, first of all, the rate of star formation in the galaxy, multiplied by the fraction of those stars which have planets, multiplied by the number of those planets that could support life per star, multiplied by the fraction of these planets that could develop life, multiplied by the fraction of those planets that could support intelligent life, multiplied by the fraction of those intelligent life civilizations that develop communication, or at least be detectable, multiplied by the length of time the above civilization releases signals.
Now, this all makes a lot of sense, right? If you would just work through it logically, and this is kind of the point. You need a star. You need a star that has planets. You need a planet that can support life. You need a planet that actually does have life on it. You need a planet that has not just life, but intelligent life that can communicate, that is still around. That's the point. And so what we've got to do is go through and estimate all of those different values and try to figure out what are our odds. All right,
Okay.
Let's begin.
So let's drill down into each of these.
Yep.
So the first one, the rate of star formation in the galaxy. So this was originally estimated in the 60s to be something like 1 per year. And by 1, we mean like one thing about the mass of the sun, right? Now, since the 60s, we've had lots of space missions. NASA and ESA have provided lots of really interesting data. So we now have a pretty accurate handle on this. And we think it's between 1.5 and 3.
Okay, so that's 1.5 and 3 per year, new stars being spat out of the star-forming bits of the galaxy. Why do we need to go for new stars, though? I mean, why? I don't quite understand that bit. Why can't we just look at stars with planets around them?
Well, because we have to look at sort of now. It's important that we think about the time period. We've only been around for a very short amount of time as humans, and we've been able to communicate with the universe for an incredibly short a period of time, only a few decades.
Right. Okay, so you need to be looking at a rate, not a number.
That's
Yeah,
right.
that makes sense.
So the rest of the numbers are fractions of those stars. So, for example, you've got fractions of those stars with planets. So we originally in the 60s didn't really have a good handle on this. We hadn't found any exoplanets
it's
at
an
that point.
utter guess.
Yeah.
And so what did they guess back in the 60s?
So they guessed somewhere between 0.2 and 0.5.
So 0.2, so 1 in 5 to a half of stars have planets, is what the guess was.
Mm-hmm.
What do we know now?
Well, we know actually that it's about 1.
Right. Pretty much every star has a planet.
Yeah,
give
this
or
has
take.
come from microlensing, from Kepler, etc. So we have a pretty good handle on this number
It's
as well.
really common. Okay.
Yeah.
Lots of planets around stars. Good. Next.
All right, next one. The fraction of planets that could support life per star, the number of planets that could support life.
All right.
Per
Now, again,
star.
back in the 60s, I mean, we hadn't even found planets around other stars yet. So how the hell do you guess that? I mean, that, are they just sort of saying, well, our solar system has got 1 out of 9 at the time because Pluto is still a planet. So did they just go for 1/9? What did
They
they
were
do?
pretty optimistic, actually. They said somewhere between 1 and 5.
Okay.
I guess they were also counting things like Mars, the
Sure.
moons of Jupiter.
Yeah.
So I guess you can sort of make some arguments that life may exist in other places.
All
in
right.
the
So they've
solar
been
system.
reasonably generous on that.
Yeah. Now, since then, when our new understanding of exoplanets, we've actually had to drop this number down quite a lot.
Oh, okay.
So we're looking.
Is that because planets like ours are actually less common than we thought?
Yeah, and planets in the habitable zones seem to be less common than we
Right.
originally anticipated. So this has dropped all the way down to 0.4
Right.
now.
So we were good on we were pessimistic about the number of planets, but we were optimistic about the whole habitable thing.
Now, remember that still accounts to a lot of planets.
Yeah.
I mean, Kepler estimates that there's 40 billion Earth-sized planets in the habitable zones of sun-like stars or slightly cooler stars.
Okay. So we're not running short of them.
Yeah.
Okay.
We've
We're
still
still
got
looking
them.
good.
Yeah. Okay. The next one is the fraction of the above that actually develop life.
Not an easy one to guess given that we have an n of 1 in the universe.
Yeah, now this is an important dividing line in the Drake equation
Yep.
because we're talking about the difference between the astronomical parameters and the biological parameters.
Yes, that's where it gets a little messier.
It does get very messy. So I would argue the astronomers have done a really good job
That's right. Okay, over to you, biologist. Come on.
at nailing down our ones, but these other ones are
So there's a
pretty
bit of a crowbar separation in the whole equation here, which is we're doing really well, and now let's start guessing like mad. I mean, the biologist must know something.
Well, we've got a sample of 1.
Yeah, which
Now-
is difficult.
Now, this number 1 is the same in the 60s as we estimate today. We don't
Right.
really have a good handle on it.
Well,
but-
we haven't found any other life, so experimentally we've still only got 1.
Yeah, and we do have some arguments as to why it might be 1. All planets that can develop life do.
Right.
The geology, for example, on Earth suggests that life arose pretty much as quickly as it possibly could have.
Okay. I mean, it did. If you think about it, on astronomical timescales, we're talking, millions, hundreds of millions, billions of years. Then again, it did happen fairly quickly. Like, you've got Big Bang, you've got stars, we've got eventually our star, the sun, you've got a planet, and then it wasn't like, we had to wait 50 billion years for life to come around. It kind of, planet cooled, life happened.
Yeah, so we estimated pretty much as soon as life was possible on Earth, it happened.
Okay. And so based on our N of 1, you kind of got to be a little bit hopeful and say, well, if it can happen, it's gonna.
Yeah, and now the counter argument to this
Mm-hmm.
is that all life on Earth has a single origin.
Yeah.
So does that mean that there was one bit of life that sprung up coincidentally very early on in the history of the Earth and then everything grew out of that?
And it just took off. It was a really good idea that kept on going, but it was just that one.
Or, is that just chance?
Yeah.
So
Yeah.
don't know is the short answer.
I mean, is the kind of life that occurred on Earth, is that the best way to do it? And it's who knows? That's really hard
It's really, really hard.
with an N of 1.
Shall we move on?
Yeah.
Okay.
So hang on, what are we estimating for that value?
1.
1. So we're assuming still that if life can happen, it will.
Yep.
Okay, well, that's probably as good as we can do.
Yeah. Now the next one gets even worse.
Mm-hmm.
The fraction of planets that develop life, that develop intelligent life.
Yeah. Okay. So so how do you do that? Now we're getting the psychologists involved.
Well, I mean, it's really, really hard. I mean, the arguments for this number being low would be that there are billions and billions of species on planet Earth, one of which we class as being intelligent.
Okay. That's
Okay.
a bit speciesist, but sure.
Maybe that number should be low. the argument for that number being very high is that generally evolution of life has led to higher and higher complexity of organisms. And so we're just at that first level of complexity that's able to support intelligence.
Depending on whether you're feeling optimistic or pessimistic, where we sit in the entire evolutionary chain. Are we the end point and it's all over, or are we just the beginning?
So I guess in the 60s, we sort of went with this idea that life does evolve into higher and higher complexities, so therefore it's going to happen eventually. You're going to have intelligent life. We're now a little bit more cagey about it. I think there's a lot more evolutionary biology we understand. Things like explosions of life. I mean, one of the famous ones is the Precambrian explosion. Do you need to have mass extinctions? What conditions did those occur under? What are the other influences? So the rare earth hypothesis sort of folds in here. Is it just that the planet Earth happens to have all this perfect Goldilocks sort of set of events that have happened to it over its history that have let life, and therefore intelligent life, evolve?
It's really hard to tease that one out, isn't it? I mean, there's this anthropic principle, which is we are here looking up at the heavens, wondering because we are in a position to do so. And maybe that's just incredibly fortunate. But you've kind of got to turn that one around and go, well, okay, but that's an end point of an argument. So let's hope not and see what else we can figure out. So what do we put on that particular factor?
Yeah.
Yeah, but you've got to quantify that. You can't just put into the equation. So what do we put into the equation?
I've got a question mark for modern day times, actually.
Okay, all right. We just don't know. So we guess.
We could go with the one from the 60s. They were pretty confident with that.
Okay, so back in the 60s they said, if it can be life, there will be. And if there is life, it'll get intelligent eventually.
Yeah.
Well, it is optimism. There you go. All right.
Okay, the next one. I'm sorry, it's only going to get worse.
Because, okay. Next.
The fraction of intelligent life forms who develop communication or develop some sort of technology that we can detect from another place.
Right, so they may not be actually trying to communicate with the universe, but they're doing stuff that we'd be able to detect from a distance anyway.
Mm-hmm.
They're watching Seinfeld on television and we can see the radiation of that signal coming out into the universe. And
we've got a lot to be embarrassed about.
We have. Sorry, universe. Sorry about that. Okay, so what do we do with that?
Well, if we're looking at ourselves, we don't actually broadcast huge amounts out into the universe.
We don't. I mean, the planet's glowing with our effect, but we're not doing it in a coordinated fashion.
And we're definitely not doing it deliberately very much.
No. In fact, not very much at all.
No, there's only been a few examples where we've deliberately broadcast signals in high strengths, basically, out into the universe. One of which was the Arecibo message in the 1970s. So we can talk a little bit more about that later when we talk about what we might want to do with this podcast.
Yes, hold on to that for a second.
But the point here is that we haven't done a lot of deliberate communication out there. So if we take our example, then this number has to be low.
Right, yeah. I mean, we have the capability, but we're just not doing it. It's interesting, isn't it? Why are we not doing it?
Well, we're more focused on searching, I think, than broadcasting. I think there's a kind of
but hang on,
self-preservation thing here.
But if everyone does that, like if no one's broadcasting and everyone's searching, no one's going to see anything. Like, doesn't it kind of follow that if no one's doing it, then we're not going to? Okay. Right. So what number do we put on that?
Well, in the 60s, they put something between 0.1 and 0.2.
Right.
We suspect now that that's actually a whole lot lower. Right. So less than 0.1.
Okay. So the likelihood of an intelligent, capable life form on another planet actually broadcasting to the heavens, we think's pretty low.
Yeah.
So currently we think they're out there in this equation. They're out there. They're just not talking to us, is the bottom line.
Yeah. Or the likelihood of us being there at the time when they are talking.
Right.
Low.
Yeah. Okay.
So last one.
Which
is actually reflecting that. The length of time of release of signals.
Right. So this is an intelligent life on another planet which is deciding that it is actually going to start talking to the universe. For what length of time? Is it sort of, we did it for 6 months and then we gave up? Is it we did it over thousands of years and just set the broadcast on repeat, broadcasting Seinfeld forever? And so what did we think about that?
Well, in the 60s, they were again very optimistic that civilizations would just
It was
be
an
out.
optimistic time. There was a lot of drugs going around and people were,
Yeah, it's
excited.
interesting.
Yeah.
So they guessed anywhere between 1,000 years and 1 billion years.
Wow. So we're assuming that the civilization's going to grow up and it's going to mature to a technology where we can start trying to communicate, and we'll keep doing it because this is really important. This is a defining part of what we do as a species. We're going to show ourselves to the universe, and we'll do that for a millennia or hundreds, thousands, millions of millennia. Really?
Well, I think nowadays, since the nuclear age, we've kind of tempered that expectation.
And then the bombs came along, and that was post bomb, but it was pre or just kicking off into the Cold War, right? Which is the 70s and 80s. And, America and Russia looking at each other going, seriously, just try your luck. Do you feel lucky, punk? And we realized, I think, for the first time as a species, just how fragile we are. That this could all be over in a heartbeat if someone sneezes and hits the wrong button or really annoys someone just a bit too much. And we're still kind of there. The Cold War's over, but there's still nuclear-powered governments, nuclear-armed governments posturing and pointing fingers at each other and going, yeah, okay, you just dare me, right? I'm ready to go. In terms of longevity of civilizations, the jury's still out on that one.
And then the modern universe, the modern world we have now, we're very sensitive to the fragile nature of the Earth itself.
There's that too.
Can it actually support us as humans the way we use it as we do? And the answer is resoundingly no, not in the current model. So how long have we got before the Earth is trashed? Well, definitely not 1,000 or 1 billion years, right?
Yeah. So there's the optimist-pessimist thing, isn't there? There's the optimist thing, which is we are capable of keeping ourselves as a species going and keeping our planet going long enough to be able to prioritize communicating with the rest of the universe. The pessimist one is, you know what? Pretty much all intelligent life is probably going to destroy itself reasonably quickly. Human beings, Homo sapiens, haven't been around for that long. It's, hundreds of thousands of years, not millions. And so is it possible that within 1 million years we've nuked ourselves or climate changed ourselves out of existence? Some people would say there's a reasonable chance of that. And maybe that's the way all life would go, that it ultimately just burns itself out, which is depressing.
It is. So I think nowadays we'd put a lot shorter time frame on that.
The 60s flower power optimism of the Drake equation has been somewhat curtailed, I think it's fair to say. So what do we put on that now? Is there a number?
I mean, you can put an order of magnitude.
Yeah.
I mean, we could start with 100 or 1,000 years. I would say would be pretty much.
Before we just nuke ourselves to oblivion. Okay, so when we multiply all... Because that was the last term, wasn't it? Is how long we keep communicating with the universe. So if we multiply all of that together...
Yep. And now you also have to fold in the number of stars.
Yep.
So that's sort of the given number. And
Right.
we know that number for quite a long time.
The number of stars in the galaxy.
In the galaxy,
Yep.
yeah.
Okay, so in the 60s... when they took all of their numbers and multiplied them together, what did they get? N equals, and N was the number of civilizations out there now trying to communicate with us.
In the galaxy, yes.
In the
So
galaxy.
you get a range.
Yep.
So you get anything from 20
Yep.
to 50 billion.
Sorry.
Sorry, 50 million. 50
Anywhere
million.
from 20 to 50 million. Okay, so the 20 side of that, look, that's not zero, right? That's okay. But if you look at the sheer vast magnitude of the galaxy, spotting one of those 20, that's not going to be easy, right?
No.
So that's basically zero.
Yeah.
But 50 million sounds doable. That sounds plausible that we could spot one of them.
Yeah, actually, I should work out how many civilizations that is per, parsec or something
Yeah.
like that, per volume
Yeah.
of space. I suspect they'd still be quite far away on average.
Sure. But it sounds
But
like the
it's-
sort of thing that you could say, no, let's do it. And so if you take sort of the median between 20 and 50 million, then you're talking potentially millions. That sounds plausible in a 60s flower power, lots of astronomers taking drugs kind of way. So, okay.
And that's how SETI sort of came, and that's the arguments that SETI uses to this day, that, we just don't know the numbers. It could be as high as this number. So SETI, which is the Search for Extraterrestrial Intelligence.
Right, and that's a whole thing in itself. Like that's capital SETI,
Yep.
and that's that's a profession that some people have on this planet. Of we're the life hunters of the universe.
And they use radio telescopes to search for unusual signals in the universe.
Yeah, that's Jill Tarter she's the big name in that, isn't she? She was the inspiration for the Carl Sagan book and then film Contact, as this amazing astronomer who ultimately finds signals from other life in the universe, and it becomes this amazing adventure. Have you seen the film, by the way?
Yes, yeah,
I've
I
only
love
read the book. I haven't seen the film.
Lovely film.
Jodie Foster, wasn't it? Okay. But that was 60s astronomy, 60s Drake equation. So what do we get now?
Well, although we have much more precise values for, say, the first three parts of the Drake
Yes,
equation.
so astronomy has done its job.
Woo, success. We have also very little new about the second half of
Okay,
it.
so I mean, it kind of breaks down into three parts, doesn't it? It's astronomy. Okay, big tick, thumbs up, well done, astronomy. You've nailed down your part, and then we get into biology, which is so biologists. Do you understand life yet? Not really. Okay, have you made it again? No, no. All right. So we're still guessing at that one, and then the end part of the equation is sociology, anthropology, human history, optimism and pessimism. And I don't think we've got any big answers about that one. So what do we get to with our best estimates?
Pretty much exactly the same number.
Really? Oh, damn it. We're still sort of it could be a few, it could be a lot.
Yeah.
Effectively none
maybe
to many.
some more arguments to be at the pessimistic end of that. But
Right.
yeah, we just don't know. And personally, I don't think we will know these numbers until we find, ironically, the other life that we're looking for in the universe.
But I mean, that's interesting, isn't it? Like, let's say tomorrow there's a discovery which no one talks about because you wouldn't, right? The first thing that you would do is, okay, shh, don't tell anyone, but I think I've seen something. Everyone point your telescopes to this, and a whole bunch of astronomers would do that, and then probably governments would get involved. And eventually, someone might announce to the rest of the 7+ billion people on the planet, hey, guess what? We've found evidence of other things out there. And that would be amazing. That would change our view of the cosmos. But that goes from an N of 1 to an N of 2. And that doesn't necessarily really help us to narrow down this equation, because it tells us that we're not alone. Great. But is that 1 out of 20? I mean, the chances of that is very, very, very slim. But it doesn't help us to figure out whether, was that incredibly lucky, or was that inevitable because it was the 1 out of the 100 million that are actually out there? We still don't know.
No.
Like, that's not a sample. That's a lightning strike. We don't know. So even when we do discover it, the Drake equation is still filled with question marks. We just don't know. What do we do with that?
You'd have to know a lot more. So we need statistics really to solve a puzzle like this, right?
Yeah.
And until we get those kind of statistics, which who knows if we ever will, then that's what I love about the Drake equation. It's a fantastic example of a thought experiment of how you do lay out a Fermi problem, which, by the way, not all Fermi problems are as, undefinable as this one. Right?
No. I mean, if you do go and do, the classic one that gets thrown about is how many piano tuners are there in New York? And you can actually get fairly close to the actual answer. I mean, you can find out the answer. You can go and count the number of piano tuners there are in the city of New York and compare it to the guess, and you can actually get quite close to that. But that's all based on a whole bunch of assumptions which we can nail down fairly well. Like, how often do you find a household with a piano in it? You can make those kinds of guesses. With this one, it really is throwing our hands up in the air on some of these and going, I don't know. What do you think? I haven't got the foggiest. Maybe we'll never nail some of those down. And what I'm really curious about is how is this seen in astronomy? Because we've talked on this podcast a number of times about one of the great things about astronomy is that you can use statistics in your favor. That things that are very rare can actually be studied because the universe is really big and full of stuff, right? Supernova, classic example, right? Don't happen all the time, and for any given star might happen once if you're lucky. But because there are so many stars in any given galaxies and so many galaxies, we're going to see them pretty regularly. Classic example. This is kind of the other side, which is we haven't got the foggiest how much this should come up. It's almost anti-science in a way. We can't answer some of these questions. So where does this fit into astronomy? How do astronomers deal with the Drake equation?
Well, yeah, some astronomers really hate the Drake equation. let's be honest, because it is a very narrow view, and I get that. I mean, if we were to really redo the Drake equation today, which some people have tried to do, then we would incorporate a lot more about what we do know in the universe. So, for example,
well, that makes sense. You go, what's that classic story of someone who's outside searching for I don't know, a lost cufflink or something. They've dropped a coin. And they're searching under the street light out on a dark street. They're searching around for it, and someone says, "Well, where did you drop it?" I dropped it over there. Well, why are you searching over here? Well, because the light's better over here, right? Boom, boom. But the point here is that if you're going to redo the Drake equation, you fill it full of stuff that you can find out, and you try to shunt away as much of the stuff that you don't know as possible. You look where the light is and see what you can work out.
Yeah. So one of these attempts, for example, is called the Sagan equation.
Okay.
Because of course he had the Seeger equation. So this is someone else who had a crack at it, included things like biosignatures. Does that count as life? Try to parameterize things like colonization of other planets. Does that happen? The idea that life might disappear and reemerge in places. So if we did wipe ourselves out here on planet Earth, would another new start of life get going and become intelligent?
Right. I mean, if we mess up horribly, people talk about the planet Earth and we're destroying planet Earth. Look, long term, whatever we do, Earth's going to be fine. It's the life that we have on Earth at the moment may have some issues, but I can pretty much guarantee you that in 1 million years' time, something will be here. May not resemble anything that we've got here at the moment, but Earth's going to be fine. It's the biosphere that we have at the moment that has a problem. So that's interesting. But I'm not sure that anything that you've just mentioned is any easier to figure out. We don't even have an N of 1 for colonizing other planets.
No.
We've got guesses based on science fiction and fantasy for that one. So that's not getting us any closer to a scientific answer.
No, but it does sort of broaden the scope a little bit. Maybe it gives you a little bit more leeway. So maybe you can pump up those numbers a little bit in ways you couldn't before.
So is this actually taught in astronomical courses? Is the Drake equation part of an astronomy degree?
Yeah, I teach it in my planetary science module.
Yeah. So how do you approach it? You can't possibly approach it as, okay, kids, let's go and figure out how many there are. How do you approach it?
I approach it as a Fermi problem, which is useful, and particularly the astronomical side of it is very useful. And historically, we've done very, very well.
As you said,
part of it,
the astronomy part's
we're proud.
Fine.
Yeah, I mean that's good, and we can apply that in lots of different other areas. If you want to know how often a supernova goes off in our galaxy, you apply a very simple problem, right? I say how many stars are there, how many are going to be of the type that are going to go supernova, what timescales do you need? So this kind of problem is very, very common in astronomy, and it's how we work out what we can and can't see.
Yeah. So it's a really useful skill, and the Drake equation captures a really compelling example, and the punchline being the first third of the equation is really, really good, and so let's nail that one down. And the remaining 2/3 are, look, who knows? That's kind of interesting. How do the students take it?
Yeah, very good actually. I mean, they like this idea, and they like debating over the numbers and applying sort of human aspects to the latter part of the equation. So talking about, well, are we all going to just destroy ourselves, for example? That's always a good way to engage students, is talk about the ultimate death and destruction of the planet Earth. But so it is interesting, and it's a useful skill to have as an astronomer, and maybe a little bit more exciting than piano tuners.
Yeah. I mean, that's your classic Fermi problem, but this one's much better, much juicier. So when this first came up back in the 60s with Drake, what was his first name?
Frank
Drake came up with this one and went through the mental argument of putting it all together, and came out with something which was presumably compelling enough. What was it, 20 to 50 million? Compelling enough to say, well, this is worth a shot. And so human beings have, in the last 50 years, tried a little bit to communicate with the universe. How have we done that?
Yeah, so Drake himself actually went on and worked with Carl Sagan on an idea where we might broadcast a message to the universe that would allow other civilizations, should they exist, to pick up on it, to know that we are another intelligent, communicative civilization in the universe.
So there's a couple of questions that immediately occur to me on that one. First of all, how? How do you broadcast to the universe? Do you have to, can you just sort of send out blanket in all directions, this is us, like a beacon going off? Or do you have to point something and say, I'm going to point at this star?
Well, it was done as part of the opening of the Arecibo Radio Telescope in 1974, actually.
That's the huge one that's sort of embedded in the top of a mountain, isn't it?
Yeah, 100 meters across. It's got a little bit damaged, actually, so it's still under repairs, I think, at the moment. But big radio telescope.
Would you say it was 100 meters across?
Yeah.
Wow.
And so, of course, a radio telescope you can turn around and broadcast signals with, as well as receive signals from the universe. And so we broadcast a message. It was actually an image that contained 7 parts, and that was transferred into binary. And then that image, binary image, if you like, was broadcast at a very particular frequency, which is very, very important to radio astronomy.
So they'd worked this one out. It wasn't just, hey, let's grab Seinfeld and just start broadcasting that out into space. This was a very specific message done in a very specific way. So, I mean, I guess pulling it apart, binary kind of makes sense. Doesn't matter how many fingers or how many toes the life form at the other end of the message has. A base 2 system is about as simple as you can get and have numbers. So if we assume numbers are fundamental in any intelligent communicating life form, then binary's probably in there. So that's a reasonably good bet.
Yeah.
And then turning that into an image, okay, we've got to assume that that's possible. So what did they send?
So they sent these 7 images, basically. So the 7 images in order were the numbers 1 to 10, first of all, the atomic numbers for hydrogen, carbon, nitrogen, oxygen, and phosphorus.
Okay, so that's again kind of setting the scene here, because all of those elements we assume and we've measured are the same everywhere. The stuff that we have down here on Earth, it's the same stuff over there. So we're kind of setting the language of the communication here. These are our numbers, and they'd be received as, what the hell is that? Well, hang on. If this bit of the picture that kind of looks a bit like what we call hydrogen, and they're calling that number 1 element number. Okay, they're starting to put together a picture of this common language of physics and astronomy that we can talk about here, which is a very cool idea.
Yeah. So the reason why they chose those particular atomic elements was because those are the ones that are present in DNA.
Ah, right. So what were they again?
Hydrogen, carbon, nitrogen, oxygen, and phosphorus.
So that's really interesting, because not only would you be able to recognize, one hopes, that, okay, these are the same atoms that are available anywhere in the universe. So that's a common language of chemistry. But then also, maybe life is quite similar in other places. We have life based on DNA. Maybe they do too, or they have something kind of similar. So you're communicating 2 things there. One is, this is how we draw life, and so that's a way of communicating the language. But also, either we're based on the same stuff as you, or this is what we're based on. One of the 2. Kind of cool.
Yeah.
What else is there?
Well, carrying on that theme, we got the sugars and bases of nucleotides in DNA, so
Right.
kind of giving a bit more detail about the structure of DNA. And then the number of those nucleotides that are in. So they're already up to 4, and we're still describing DNA. It's a
Yeah.
complex thing, right?
Yeah.
The double helix structure is in there, for example. You can see a little graphic of the double helix.
So it's all setting the scene. It's telling a lot about how we're communicating, but also what we are.
Yes, yeah.
Yeah.
This is us, yeah. The fifth one is a picture of a human and the height of a human.
Little stick figure.
Yeah. Plus the population of the Earth at that time.
How does it do the height?
So it was relative to the hydrogen atom.
Ah, right. So it gives, wow, that's a lot of hydrogen atoms. Okay, but I mean, how else are you going to do it?
Yeah,
right.
you need
You've got to have
a ruler
common...
that's common.
Yeah. And if hydrogen's the same everywhere, then all right, hydrogen's this big, we're this big, much bigger than hydrogen. Yep.
A graphic of the solar system showing which one we are, third rock from the sun.
Third
if you
rock
like.
from the sun. Yeah.
And finally, the
Does
last.
it give any information about where the sun is?
No.
Well, I guess, but they're seeing that, right? Because we're broadcasting this to the universe.
Yeah.
So they've already gone that one. That one there. So they know which one it is. So third planet out from that one. Yep,
Yeah.
got it.
So other spacecraft that we sent out do have that information based on pulsars that are around us. So it's kind of a map of where the sun is.
Right.
relative
So
to
on
pulsars.
Voyager, for example, it's, where did this lump of rusty metal come from that's just plummeted onto our planet's surface? Oh, right. It's from that one over there. I see.
And the final one was a picture of the Arecibo dish itself with its diameter.
Oh, right. Okay. So this is where the message came from.
Yeah.
Right. So here's the common language, all about us. This is how big we are. And then this is where the message has come from. Cool. Nice one. And so presumably, because we are an intelligent and peace-loving species, we've been broadcasting this constantly since we came up with the idea in all possible ways.
No. No, we broadcast it once in one direction only.
Right. Okay. So this wasn't exactly a comprehensive communication strategy and more of a PR stunt.
No. It took 3 minutes, and we pointed the dish at a globular cluster, which is a dense grouping of stars called M13.
Mm-hmm.
No.
3 minutes.
Yeah, 3 minutes.
Yep.
That's all you get.
Okay.
So if you're not intercepting that...
If you didn't happen to be listening at the time, it's gone.
The hilarious thing is, so it's going to take 25,000 years to reach the cluster because it's 25,000 light years away. And
Right.
radio signals travel at the speed of light.
And when was this done?
This was done in the 70s.
Right,
74.
so we're 45 years into that.
So 24,000.
25,000 years to go. Yeah.
Yeah. Okay. The hilarious thing is, actually, the cluster's going to have moved a bit since then.
Damn it. We didn't think of that.
Not so much that it'll have moved off the cluster, but the core. We won't be
But it's not
broadcasting to
pointing
the core anyway.
So not only is it for 3 minutes total, but in 25,000 years' time, it will be hitting a significantly lower number of the stars in that cluster. Well done, all.
And a globular cluster is probably a terrible place to point such a signal.
But as a PR stunt, really good idea. I'm sure that captured a lot of imagination.
Well, at least it was kind of tempered so that I guess the likelihood of there being an intelligent life form in this globular cluster, because the stars are really old, right? So the chances of life being there is kind of dubious. It was kind of pragmatic, maybe, that, okay, we're going to send this signal out. It's really to celebrate Arecibo.
Yep.
We don't really want the aliens to come and find it in case they come and blow us all up. So we'll just point it at something that maybe doesn't have life in it.
Yeah. Did people sort of turn around and go, excuse me, Mr. Sagan, Professor Sagan, have you really thought this one through? Like, what if they do come and get us? All right. We'll point it at this thing because it's not going to work anyway. Just 3 minutes. Trust me, it'll be okay. Right. So that wasn't a serious attempt. Have there been any others since?
Well, there's going to be one very, very soon.
Well, there is. I'm not sure how serious it is, though.
Well, I think we can maybe cut through all of this nonsense of trying to work out what hydrogen is and what DNA is.
Yep.
We can just directly broadcast this episode.
I think that's an excellent idea. You know what? And if we can do that, if we can send episode 42 of Syzygy to the stars, then whoever receives that will learn so much about our species. I think it's far better than giving them information about DNA and about sizes of telescopes and so on. They're going to learn about our inherent curiosity, don't you think?
About bizarre Australian and New Zealand accents.
Exactly. So I think it's got to be done. All right, damn it, we're going to do it. This episode is going to be broadcast to the stars. We're going to have to figure out where we're going to point this thing. How are we going to do it? Got so much to work out.
Yeah. Somewhere we can look up and wonder.
All right, I guarantee you, listeners, by the time you are hearing this, you won't be the only ones that are going to be the recipients of this. We're going to send this out into the universe. We're going to broadcast episode 42 of Syzygy to the cosmos and be heard on other sides of galaxies and other galaxies forevermore as it beams off across the universe at the speed of light. That's pretty exciting.
And if you are listening out there, please do give us a 5-star review. It really does help us out.
Oh dear, well who knew when we started this episode that it was going to turn into something quite so epic? I think that's a fabulous idea. We have to do this. We're going to do this. It is done by the time you're listening to it. Episode 42 is going out there at the speed of light into the cosmos. Emily, how does that feel?
Exciting, and also I'm really sorry, universe.
Yeah, exactly. Well, I'm sorry, universe, and I'm sorry to the rest of our species if the universe turns around and says, hang on, we've got to go and invade them and wipe them out because we can't have any more of that. That's just wrong. So I apologise for our impending doom if that's, the ramifications of this. But look, we had to give it a shot.
It could go the other way too. I mean, everyone could come and join in. We could be just a happy galactic civilization.
Well, that's true.
With amazing new technologies and understandings.
There's a middle ground, which is that we never hear from any other civilization out there in the cosmos ever again because of this episode. We don't get invaded. We just get shunned forever because of episode 42 of Syzygy. Let's go with the optimist and say that we're going to be getting feedback. Positive feedback, questions coming from, I don't know, Alpha Centauri or something sometime soon. So that would be very cool. But closer to home, if you want to get in contact with us, there's plenty of ways that you can do that. You can do it through the Twitters, Emily. How do they do that again?
We are at SyzygyPod. Mm-hmm. You might need to add a dialing code in front of that if you're from another galaxy.
That's right, yes. I don't know, do they have Twitter out there? Who knows? Yep, at SyzygyPod. You can find us at SyzygyPod most places. Send us a question, send us your comments, send us your thoughts. Just don't send us your invading alien spaceships. That would be bad. You can go to syzygy.fm and find all of our past episodes, show notes, lovely images, all of that sort of thing. All the way back to episode number 0, where this all began a bit over a year ago.
And it is inevitable that any civilization is going to develop Facebook.
Yep, so you can find us on
Instagram.
Facebook. Just search for the Syzygy Podcast or at SyzygyPod. We're on Instagram or on Instagram, all of the social medias. And you don't have to be around another star or in another alien civilization to leave us 5 stars as a review. It helps us to rise up through the noise, and more people can discover our nonsense about the cosmos. Speaking of nonsense about the cosmos, that's all we can do for this week. We're going to catch you in about a week's time or so for another edition of the universe's favourite astronomy podcast, Syzygy. We'll catch you next time. See you later, Emily.
See you later.
Bye. So as we beam episode 42 of the Syzygy podcast out across the universe in the general direction of Betelgeuse, we'd like to take the opportunity to thank everyone who's made the last 42 episodes of this podcast possible. We'd like to thank the University of York for giving us the space and the time, particularly Emily's time to do this. We'd like to thank Mark from Astro Campus for putting in all the effort to actually do the beaming out across the universe. And we'd like to thank our wonderful Patreon patrons, Russell Townsend, Joshi D, Chris Baker and Sho Fuji, for pitching in the dough to actually make the podcast possible, to keep the lights quite literally on. Thanks everyone. We really do appreciate the support. Thanks for listening.